Object detection on edge devices, such as microcontroller units, is crucial for reducing detection latency and increasing overall energy efficiency. However, classical object detection deep neural networks like YOLO, RCNNs, or SSDs are not suitable for deployment on microcontrollers due to their high memory requirements. To overcome these constraints, techniques like pruning, quantization, and neural architecture searches have been proposed. This paper introduces TinyissimoYOLO, a novel, highly flexible, quantized, and ultra-lightweight object detection network designed for microcontrollers with power consumption in the order of milliwatts and less than 0.5 megabytes memory available for storing convolutional neural network weights. The proposed quantized network architecture has 422K parameters, enabling real-time object detection on embedded microcontrollers. TinyissimoYOLO is trained using quantization-aware training and deployed with 8-bit quantization on different microcontrollers, achieving high frame rates of up to 180 fps and ultra-low energy consumption of only 196 microjoules per inference with an inference efficiency of more than 106 MAC cycle. The network is composed of quantized convolutional layers with 3x3 kernels and a fully connected layer at the output, designed for a low memory footprint of less than 0.5 megabytes. The proposed network is evaluated on the wider face dataset and demonstrates multi-object detection capability with up to 3 classes, showcasing its flexibility and adaptability. Notably, adding object detection classes will increase the size and memory consumption of the network. The deployment of TinyissimoYOLO on the MAX 78000 microcontroller, exploiting CNN accelerators, further highlights its potential for edge processing and edge artificial intelligence on resource-constrained microcontrollers. The paper introduces TinyissimoYOLO, an ultra-lightweight object detection network designed for deployment on microcontrollers, micro-Cs, with a memory envelope of 0.5 megabytes. Inspired by YOLO-v1, it is optimized for CNN accelerators in recent micro-Cs, such as the MAX 78000 from Analog Devices. TinyissimoYOLO's architecture includes an input image size of 88 by 88 pixels, hidden convolutional layers, a fully connected linear layer before the output layer, and an output layer size of 4 by 4. The network uses a YOLO-v1 output format with B equals 2 bounding boxes for detecting objects in the wider face dataset. For multi-object detection in Pascal Vogt, B equals 1 is chosen to ensure deployability on the MAX 78000 CNN accelerator. The network's hidden convolutional layers utilize 3x3 filters to minimize weight memory, starting with 16 output channels in the input layer and increasing to 128 output channels at the output. Max pooling with a stride of 2 decreases the channel resolution every second layer. A fully connected linear layer predicts output probabilities and coordinates from the features extracted by the convolutional layers. TinyissimoYOLO is trained using the YOLO loss function introduced in the YOLO-v1 paper and evaluated using the mean average precision (MAP) metric. The network is trained and tested on the wider face dataset, with 90% of the training dataset used for training, 10% for validation, and the corresponding test dataset for evaluation. The paper also investigates the effect of MAP against relative object size dimensions within images, helping to understand the optimal object size for training the generalized object detection network. TinyissimoYOLO is a novel neural network designed for efficient object detection in real-time scenarios on low-power devices, such as microcontrollers and CNN accelerators. To ensure accuracy in detecting visible objects in downscaled images, the network is trained on a subset of the wider face and Pascal Vogt datasets, with restrictions on the number of objects per image. The network's performance is evaluated using mean average precision (MAP) metrics, demonstrating high accuracy when trained and evaluated with limited objects per image. Notably, TinyissimoYOLO achieves up to 73% MAP on wider face and 57% MAP on Pascal Vogt datasets, respectively, outperforming previous models. To facilitate deployment on microcontrollers and CNN accelerators, the network is optimized for specific constraints, including a 442 kilobytes weight memory footprint and input size limitations. The MAX 78000, a representative micro-C, is used as a target platform. A full pipeline demonstrator is built, integrating the MAX78000FTHR Micro C with an on-device image sensor, camera cube chip, to validate the system with real-life data. This optimized design enables efficient object detection in real-time scenarios on low-power devices, making it suitable for applications that require fast and accurate object detection, such as autonomous vehicles, surveillance systems, and robotics. The TinyissimoYOLO network is a multi-object detection model optimized for edge applications, specifically designed to detect a small number of objects simultaneously. It can be deployed on any microcontroller, Micro C, with a minimal required flash of less than 0.5 megabytes for its network parameters. Evaluations have shown that training the network on input images with objects adequate for its input size, restricting the dataset to maximal 10 or 5 objects per image, increases not only network performance on a restricted evaluation but also when evaluating the network on the original validation dataset. This results in up to 45% mean average precision, MAP, for wider face. When evaluated on a restricted Pascal Vogt dataset, the network achieves 59% MAP with 57%, 30%, 65% on the classes person, chair, car respectively. Comparing low-power Micro C devices when running the TinyissimoYOLO network reveals that the MAX78000 accelerated hardware is the most energy efficient among the evaluated devices. It is able to achieve fast inference times running in real time on Micro Cs with speeds up to 180 fps. The network's performance is evaluated on various metrics such as power efficiency, microwatt per megahertz, inference efficiency, MAC, cycles, inference latency, MIS, and energy per inference, MJ, INF. The results indicate that the MAX78000 outperforms the others by a factor of greater than 65x in terms of latency, inference efficiency, and energy per inference. This page concludes the research paper with a comprehensive list of findings, highlighting novel applications of machine learning in environmental monitoring. It emphasizes the significance of integrating AI-driven algorithms for predicting and mitigating the impact of climate change. The section details the development of a new predictive model, leveraging satellite imagery and real-time sensor data to forecast environmental degradation.